So next up we have Professor Jake Abbott, and he's with us. I already checked, which is great. So this is Jake Abbott is a professor in the Department of Mechanical Engineering and an adjunct professor in the College School of Computing at the University of Utah. And he's the director of the Magnetic and Medical Robotics Laboratory. So from big humanoid robots to small micro robots. He did his postdoc at ETH Zurich and his PhD at Johns Hopkins University back when Alice Okamura was still there. His focus is on wireless, magnetic controlled microrobots with dexterous non-contact control. He has a career award, an NSF career award, a number of best papers and best poster awards. So please take it away, Jake.
Thank you. Can you hear me?
Yes, we hear you well.
Great.
Very nice background.
Thanks. Just get it in presentation mode. Okay, yeah, so when I was asked to speak today, I thought of two projects that are going on in my lab that I think sort of exemplify this idea of embodied intelligence, and they're targeting two different application spaces, but they use a lot of similar principles, which I'll come back to at the end. Okay, so both of these projects in my mind are simple and soft, magnetically actuated medical robots. Just really quickly to make sure everyone's on the same page, when we're talking about using magnetic actuation, we're talking about separately about magnetic torque and magnetic force. And how this works is if you have a little magnetic object in a magnetic field, it will attempt to align with the local magnetic field, that's magnetic torque, and it will attempt to move to higher strength fields, and that's how force is generated. We see that torque is proportional to field itself, whereas forces are proportional to spatial derivatives in field. And that is an important factor as you think about scaling things from a benchtop to clinical settings. When we make the field, all of the projects that I'm working on currently are using dipole field expression. So rather than surrounding some workspace with electromagnets, for example, we're talking about using just one strong magnet that can be positioned in space using some sort of robot. This scales well for our clinical use because you don't have to make a set of electromagnets that can completely surround a human body. Rather, you can put this magnet right next to a patient. And when we think about a dipole field, the important thing is we see that the strength of the field scales with 1 over distance cubed. That means torque also scales with 1 over distance cubed, but it turns out forces scale with 1 over distance to the 4th because of that spatial derivative. So forces scale worse than torques. So if you can use torques, you should. And this sort of dipole model is perfect for simulating spherical permanent magnets, and it's a good approximation for almost any other magnet if you're far enough away. Okay, so the first thrust I'm going to just briefly talk about is this idea of endoluminal devices. So this is the idea of you're shoving some long continuum structure through some existing channel. You can use it for your gastrointestinal tract, different catheters in your vasculature. And we've done a lot of work in my lab on cochlear implant electrode arrays, where you're shoving an electrode array into a spiral structure. A well-known problem with these sort of endoluminal devices is this balance between being too stiff and too soft. If you're too soft, what happens is as you push in, you will eventually reach a point where there's enough friction buildup that your device wants to buckle rather than inserting farther. And if your device is too stiff, then it won't conform to the natural lumen. And so one thing we kind of stepped back and said, this problem, this well-known problem, it really all stems from our reliance on pushing the device in from the proximal end. So if we can move away from that sort of pushing philosophy, we can sort of circumvent this problem. So we came up with a really simple kind of physics where you say, if I take a continuum structure and I embed permanent magnets in it, and those permanent magnets have oscillating magnetization, or alternating, I should say. So each magnet has reverse polarity in terms of its north and south. And then I sweep a rotating dipole field over it, it will induce an undulatory kind of inchworm locomotion that will cause crawling in a deterministic direction. And in this plot in the lower left, what I'm showing you is that if we compare the use of the dipole field and the alternating magnets to a dipole field with non-alternating magnets or a uniform field and alternating magnets, This combination is special. The dipole field combined with alternating magnets, it leads to much more efficient locomotion. And a cool thing about this is you can extend it so it doesn't just work for 2 magnets. You can keep stacking these magnets along the length of a structure and keep alternating their magnetization. And with very sort of almost non-existent localization, you can induce a kind of crawling undulatory locomotion that you can use to help yourself insert things essentially limitless in terms of depth. We can't find a bottom of this structure, basically. And you're kind of just gently inserting it, and you're kind of just putting a biasing force, and then you're letting the oscillation do most of the crawling. Now, because of time, I want to switch gears quickly to this topic of steerable needles. So I'm sure many of you have seen steerable needles of various kinds. They typically work by some sort of beveled tip. So as you insert a needle into soft tissue, the needle will naturally curve due to this bevel tip, and then you use rotation of the needle to steer. And people have tried lots of different designs to try and make these steer better. You can kink the tip. You can put various hinges on them. You can use micro machining processes to make your needle more flexible. There's all sorts of different designs. And why might we want to do this sort of steerable needle type of device? Well, here's a motivating example. If you're treating epilepsy in the brain, what you want to do is you basically want to thermoablate, meaning kill the hippocampus and the amygdala of the patient. But if you come in with a straight needle, you're not going to be able to get everywhere you want to get. And studies have shown that people really get only very partial ablation of these structures because the straight needle just doesn't let you access them. So if you have a steerable needle, you can imagine having one insertion point, but still being able to tackle a lot of different regions inside this. So this is the type of thing you should imagine in your mind. So here's some traditional steerable needles. And I want you to watch the region in this red box and the region in this red box as time go on. And we're pushing these traditional needles in. And what you will see, watch the left image first, and you will eventually see right here, the needle starts slicing laterally. If we watch the right image now, we see a much worse slicing laterally. And so you don't want that to happen in your brain. And why this is happening, it's again reliance on our pushing. There's a lot of friction build up along the length of the needle. And eventually that friction stops you from inserting further. And if you try and insert it further, you will get this lateral slicing. So again, the reliance on pushing is a problem. So we developed a new invention. It's a new type of steerable needle. It moves away from the pushing paradigm, and basically it comprises a screw tip, ring magnets that have a lumen, and a soft flexible shaft. We're talking about polymer tubing as opposed to a metal tubing as in traditional needles. You can make these tips out of metal. You can make them by 3D printing, for example, with a nanoscribe. But the idea is, even with this idea, we have this continuous lumen that's a working channel all the way from the tip to the proximal end. And what we're doing is we have two forms of actuation. We can twist the proximal end. We can do it with a robotic stage, which we do in our lab, or with our hands. And then we magnetically steer the tip. We've decoupled the actuation in these two different forms. So now we're converting the rotation at the proximal end into rotation at the tip. That screw pulls the needle forward. So rather than only relying on pushing, we're still sort of gently applying a pressure, but instead of relying on pushing, we're pulling from the tip, and the steering happens magnetically. So this is a video showing how this might work for that same brain procedure. This control is certainly suboptimal because we just have a graduate student he's acting as the controller and the motion planner and everything. But you can see with this type of needle, you're able to achieve the types of curvatures needed. This is an at-scale representation to do this sort of procedure. Another cool thing is we can achieve very highly expressive paths in soft tissue phantoms that no one's ever achieved sort of even close with other needles. So we can reverse curvatures. We can make S shapes. We can even double back on ourselves, turning 360 degrees, where previously it's been very difficult to turn more than 90 degrees without these slicing. And then you see that you don't have to steer in reverse. You can actually just sort of reverse your insertion profile in terms of the proximal end, and the needle will follow back over its own path. And we've shown that we can achieve much tighter radius of curvatures than existing needle concepts in soft tissue phantoms. And with our needle, it works particularly well in delicate tissues. And as the stiffness of the tissue increases, our needle starts getting worse and other needles start getting better because they are reliant on the stiffness of the tissue for steering. So this is a new paradigm for delicate tissues like brain or lung. And these two, this is my last slide, these two concepts share a few important principles that I like. They reduce our reliance on pushing from the proximal end. They utilize magnetic torque, which scales better than magnetic force for clinical use. They utilize a dipole field, which lends itself to clinical translation, just a big robot held on the end of a robot. It's pretty simple, and you can make it really strong and stay cool. The localization and the control in the roll direction along the long axis is unnecessary due to radial symmetries. Both ideas maintain a working channel because they use sort of ring-shaped magnets so that we can actually do something once our continuum device reaches its target of interest. And the simplicity, very simple components, means that we can fabricate this at a wide range of scales, what we typically call mesoscales. These aren't microscale devices, but we can make them very tiny up to relatively large. That's a good place for me to stop with such a short talk. Yeah. Thanks a lot for the invitation.